You look at a picture, right? And your brain just gets it. You see a face, a car, a landscape. But a computer? It just sees a giant, chaotic mess of numbers. So how do we bridge that gap? Today, we're diving into the really clever mathematical tricks that actually teach machines how to see. All right, so let's get right to the heart of the problem. It all boils down to pixels. See, for a machine, an image isn't really a picture at all. It's just this massive grid of numbers. And trying to find a coherent pattern in all that raw data, it's like trying to read a novel that's been written out as one single million-digit number. It's just not going to work. Take a look at this. For you and me, it's a no-brainer. It's the letter E. Our brains are incredible pattern-matching machines. We see the whole shape, the lines, the corners, and it all just clicks into place instantly. It feels totally effortless, right? But a computer, it doesn't have that amazing biological hardware we've got. So what does it see when it looks at the exact same image? Let's peel back the curtain. It sees this, a massive, overwhelming sea of numbers. That's it. Even a simple 100 by 100 pixel image turns into a list of 10,000 different values. This is what we call high-dimensional data, and it's a real headache. It's complex, it's noisy, and honestly, a lot of it is just plain redundant. Trying to teach a machine to find the letter E in all that chaos, it's wildly inefficient. There has to be a smarter way. And that smarter way is exactly what we're talking about today. It's called feature extraction. You can think of it as the art of boiling down that chaotic sea of pixels into just a few essential, meaningful characteristics. We call them features that really define what we're looking at. So instead of dealing with 10,000 noisy data points, maybe we only need a handful of really good ones. Okay, so how do we actually find these essential features? One of the oldest and most powerful tools in the box is something called principal component analysis, or PCA for short. A good way to think about it is as a method for finding the main story that's hiding inside all that numerical noise. And the way PCA works is actually pretty clever. It looks at this big cloud of data points and asks a really simple question. In which direction does all this data spread out the most? Where's the biggest variation? That direction, that becomes our new super simplified axis. By basically squishing all the data down onto this one line, we hang on to the most important information while letting go of the less relevant details. And right here, you can see perfectly when PCA is an absolute superstar and when it kind of falls flat. On the left, check it out. The direction with the most spread also happens to be the exact direction that cleanly separates the circles from the squares. Perfect. But look at the right side. The main direction of variance just mashes the two groups together into a jumble. This really highlights something crucial about PCA. It's amazing for reducing complexity, but it doesn't always care about keeping your different categories separate. Okay, so PCA gives us this big picture view by finding the main axis of variation, but it's looking at everything all at once. What if the really important features aren't about the overall spread, but about the patterns inside the image? For that, we need a totally different lens. We need to stop thinking about where pixels are and start asking a new question. What if we could describe an image by the different waves that, when added together, create it? This is the core idea behind Fourier and cosine transforms. So the main idea here is to switch domains. We're moving from what's called the spatial domain, the plain old grid of pixels, to the frequency domain. And here's an easy way to think about it. Low frequencies are the big, broad, smooth parts of an image. They're like the overall shape. High frequencies? Those are the sharp details, the fine textures, and a lot of the noise. So if we can just isolate that low frequency stuff, we can often capture the absolute essence of an object. And this is a perfect demonstration. We start with the outline of our letter E. Now, look what happens when we use just a few Fourier coefficients, which are really just numbers that describe the simplest, biggest waves. We get a blurry blob. Not very helpful. But watch. As we start adding in more and more coefficients describing finer and finer waves, the recognizable shape of the E just emerges from the blur. This is amazing. We've basically rebuilt the object using just a handful of frequency values instead of thousands of pixels. Now, there's a close relative to the Fourier transform called the Discrete Cosine Transform, or DCT. You can think of it as Fourier's more practical, efficient cousin. The big difference is that it only uses real numbers, which means it avoids some of the more complex math. That makes it way faster and easier for computers to process. And it is exceptionally good at one thing: packing the most important visual info into just the first few coefficients. All right, so let's take a step back. Both PCA and Fourier transforms are looking at the image globally. They're trying to summarize the whole picture at once. But what if the features that really matter are small and local? Like a specific sharp edge or a corner. For that, we can't look at the whole image. We need to zoom way in. We need a tool that acts less like a summarizer and more like a detective's magnifying glass. And that tool is the convolution. The heart and soul of a convolution is something called a kernel. It's just a tiny little matrix of numbers, a filter, really, that we slide across our main image, one spot at a time. And here's the cool part. Each kernel is a specialist. It has one job. Maybe its job is to find horizontal lines, or vertical edges, or corners. It's like having a whole army of tiny, specialized detectors, each one scanning the image for its own specific clue. And the results? They're pretty striking. On the left, we've got our original picture of a house. But on the right, that's what happens after we apply a special kernel called a Sobel operator, which is designed to do one thing: find edges. Look at that. The kernel has basically gone through and erased all the flat, boring surfaces and only highlighted the spots where there's a dramatic change. What we're left with is this new, super simplified image, a feature map, that is basically a perfect outline. Now that's something a machine can easily work with. Okay, so we've thrown around some pretty heavy math here. PCA, Fourier transforms, convolutions. But I want to be clear. This is not just some abstract theory from a textbook. The real question is, how does this stuff actually show up in the technology you and I use every single day? Oh, it's everywhere. I mean, literally all around us. Remember that super efficient discrete cosine transform, the DCT? That's the powerhouse behind JPEG image compression. Every single time you take a photo with your phone and save it, DCT is working its magic. And those convolution kernels we just saw, like the Sobel operator, they are absolutely crucial for the edge detection your camera uses to autofocus. And they're a fundamental part of how self-driving cars see the world. But here's the thing. There's one common thread that connects all of these classic, powerful methods we've discussed. Every single one, the Sobel kernel, the DCT, even Gabor filters for texture. They were all meticulously designed by a human. They're fixed, handcrafted mathematical tools. And that leads us to a final, really powerful question. What if a machine didn't need us to hand it the tools? What if a machine could learn to design its own filters to see the world, perfectly optimized for whatever it needs to do? Well, answering that very question is exactly what kicked off the entire deep learning revolution.